Hello guys, and welcome to my YouTube channel. In this video, I am going to explain how cryptocurrency mining works from scratch, step by step. A cryptocurrency miner is a powerful computer that performs the computational work required by a proof-of-work blockchain. The word miner does not refer only to a person. It usually refers to the hardware, software, or mining operation participating in the network. In Bitcoin mining, specialized machines called ASIC miners are commonly used because they are designed specifically to perform SHA-256 hashing calculations extremely quickly. A miner has several important responsibilities. First, it receives pending transactions from the network. It checks whether those transactions follow the blockchain protocol. For example, the miner confirms that the digital signatures are valid and that the same coins have not already been spent. Next, the miner selects valid transactions and packages them into a candidate block. This candidate block contains the transaction data, a reference to the previous block, a timestamp, a Merkle root, the difficulty information, and a nonce. The miner then begins hashing the block header repeatedly. It changes the nonce and sometimes other adjustable data to produce new hash results. All miners are competing to find a valid hash before the others. The first miner to produce a hash below the network target can announce its block. Mining is therefore not simply about creating new coins. Its main purpose is to verify transactions, create new blocks, secure the blockchain, and make fraudulent changes extremely expensive. The mining process begins when users create cryptocurrency transactions. Imagine that one user wants to send Bitcoin to another person. The sender enters the receiving wallet address, chooses the amount, reviews the transaction fee, and confirms the payment using a cryptocurrency wallet. The wallet then uses the sender's private key to create a digital signature. This signature proves that the transaction was authorized by the owner of the funds. Importantly, the private key itself is not shared with the network. After the transaction is signed, it is broadcast to nearby blockchain nodes. Each node performs basic checks and then relays the transaction to other connected nodes. Because blockchain networks are peer-to-peer systems, there is no single central server responsible for distributing the transaction. Instead, the transaction spreads across the network from node to node. Valid but unconfirmed transactions are stored in an area commonly called the mempool. The mempool is essentially a waiting area for transactions that have not yet been included in a block. Different nodes may temporarily have slightly different mempool contents because transactions do not reach every node at exactly the same moment. Miners monitor these pending transactions. They usually select transactions based on validity, size, and fee rate. At this stage, the transaction is visible to the network, but it is not yet permanently recorded in the blockchain. It must first be selected, verified, and included in a valid mined block. Before miners place transactions into a block, they must confirm that those transactions follow the rules of the blockchain. Miners receive pending transactions from their mempool and perform several verification checks. The first check is the transaction format. The transaction must contain the correct fields, structure, inputs, outputs, and values required by the protocol. A malformed transaction is rejected. The next check involves the digital signature. The miner verifies that the signature matches the public key associated with the funds being spent. This confirms that the transaction was authorized by the legitimate owner. Miners also check whether the transaction inputs are still unspent. This prevents double spending, where someone attempts to use the same cryptocurrency in two different transactions. The miner checks the available amount as well. A transaction cannot spend more funds than the referenced inputs contain. The total input value must cover both the payment amount and the transaction fee. Additional rules may include script validation, lock times, transaction size limits, and other consensus requirements. Transactions that fail any required check are excluded from the candidate block. Only valid transactions move forward. It is important to understand that miners do not decide the rules themselves. They enforce the consensus rules already defined by the network protocol. This verification process protects the blockchain from invalid payments, unauthorized spending, malformed data, and double spending attempts. It ensures that only legitimate transactions can eventually become part of the permanent blockchain history. After verifying transactions, the miner begins constructing what is known as a candidate block. The miner selects a group of valid transactions from the mempool. Because a block has limited space, miners cannot always include every pending transaction. Transactions with higher fee rates are often prioritized because the miner can collect those fees if the block is accepted. The candidate block contains two main parts, the block header and the list of transactions. The transaction list includes the selected payments, along with a special transaction called the coin-based transaction. This transaction creates the miner's block reward and sends it to an address chosen by the miner. The block header contains the information used during the mining process. It includes the version number, which indicates the block validation rules being followed. It also contains the previous block hash. This connects the new block to the block before it and creates the blockchain structure. The Merkle root is a single hash that summarizes all transactions inside the block. If any transaction changes, the Merkle root also changes. The timestamp represents approximately when the block was created. The difficulty target defines how low the block hash must be. Finally, the nonce is a number miners repeatedly change while searching for a valid hash. At this point, the candidate block is not yet part of the blockchain. It is only a proposed block. The miner must now complete the proof of work process before the network will consider accepting it. Proof of work is the mechanism that requires miners to perform computational work before they can add a new block to the blockchain. The miner takes the candidate block header and processes it through a cryptographic hash function. Bitcoin uses double SHA-256, meaning the block header is hashed using SHA-256 twice. A hash function converts input data into a fixed length output. The resulting Bitcoin hash contains 256 bits and is usually displayed as 64 hexadecimal characters. One important property of cryptographic hashing is unpredictability. Even a tiny change in the input produces a completely different output. For example, changing the nonce from one value to the next causes the block hash to change dramatically. The miner cannot calculate the correct nonce directly. There is no shortcut that reveals which nonce will produce a valid hash. Instead, the miner must repeatedly try different inputs, calculate the resulting hash, and compare it with the network target. A valid block hash must be numerically lower than or equal to that target. Most generated hashes are too high and are rejected. The miner simply changes the nonce and tries again. Proof of work is expensive to produce because it requires huge amounts of computation and electricity. However, once a valid hash is found, other nodes can verify it very quickly. This difference is important. Creating proof of work is difficult, but checking it is easy. That is one of the main reasons proof of work helps protect the blockchain from manipulation and fraudulent block creation. The nonce search loop is the repetitive process miners use to search for a valid block hash. The nonce is a field inside the block header. It is usually a 32-bit number that miners can change. The miner begins with one nonce value and hashes the block header. It then compares the resulting hash with the current network target. When the hash is higher than the target, the attempt fails. The miner increases or changes the nonce, hashes the block header again, and produces another completely different result. This loop continues extremely quickly. Modern ASIC miners can perform trillions of hash calculations every second. Each calculation represents another attempt to find a valid result. Most attempts fail because only a very small portion of all possible hash outputs are below the target. When every possible value in the normal nonce field has been tested, the miner can change other adjustable information. For example, the miner can modify extra nonce data inside the coin-based transaction. This changes the Merkle root, creating a new block header and a completely new range of possible hashes. The miner may also update the timestamp or change the selected transaction order. This allows the search to continue almost indefinitely. Eventually, one miner somewhere on the network may produce a hash that is lower than the required target. That successful hash proves that a large amount of computational work was attempted. The winning miner can then stop the search for that block and immediately broadcast the completed block to the network for verification. Mining difficulty controls how hard it is for miners to find a valid block. The network represents this requirement using a target value. Every block hash can be interpreted as a very large number. To be accepted, that number must be lower than or equal to the target. A higher target makes mining easier, because a larger range of hash values will be considered valid. A lower target makes mining harder, because fewer hash values satisfy the requirement. Difficulty and target therefore move in opposite directions. When difficulty increases, the target decreases. When difficulty decreases, the target increases. Bitcoin adjusts its mining difficulty every 2016 blocks, which is approximately every 2 weeks. The network examines how long the previous 2016 blocks took to mine. If those blocks were created too quickly, it means the total network hash rate increased. The protocol raises the difficulty, so future blocks become harder to find. If the blocks were created too slowly, the protocol lowers the difficulty. The goal is to maintain an average block interval of approximately 10 minutes. This adjustment is necessary because the number of miners and the efficiency of mining hardware can change dramatically over time. Without difficulty adjustment, faster hardware could cause blocks to be produced too rapidly, while a major reduction in mining power could make blocks extremely slow. The difficulty system keeps block production relatively predictable. It also ensures that increasing the total amount of mining hardware does not permanently increase the number of new Bitcoin blocks created each hour. Instead, the network automatically makes the proof of work challenge harder. Eventually, one miner finds a block hash that satisfies the network difficulty target. This miner becomes the temporary winner of the current mining competition. The winning miner immediately broadcasts the new block to other nodes across the peer-to-peer network. The block contains the full list of transactions, the block header, the proof of work, and the coin-based transaction that awards the miner. However, the network does not automatically trust the miner. Every receiving node independently verifies the block. The node checks that the previous block hash correctly points to the expected blockchain tip. It verifies every transaction inside the block and confirms that no input has been spent twice. It recalculates the Merkle root and checks that it matches the value stored in the block header. The node also hashes the block header and confirms that the resulting hash is below the difficulty target. The Coinbase reward is checked to ensure the miner did not create more cryptocurrency than the protocol allows. If the block passes all consensus rules, the node accepts it and adds it to its local copy of the blockchain. The node then relays the valid block to other peers. Within a short time, the block spreads across most of the network. Other miners stop working on their previous candidate blocks and begin building new blocks on top of the newly accepted block. Sometimes two miners find valid blocks almost simultaneously. In that situation, the network may temporarily split. Eventually, the chain with the most accumulated proof of work becomes the accepted chain. Miners are financially rewarded for contributing computing power and securing the blockchain. The successful miner receives two main forms of income: the block subsidy and transaction fees. The block subsidy consists of newly created cryptocurrency. In Bitcoin, this reward is reduced approximately every 4 years through an event known as the halving. The miner also collects the fees from all transactions included in the block. These rewards create an economic incentive for miners to follow the rules and continue protecting the network. However, mining a block is highly competitive. A small individual miner may operate for months or even years without finding a valid block. Although the reward would be large, the probability of receiving it is very low. For this reason, many miners join mining pools. A mining pool combines the hash power of many independent miners. Each participant performs hashing work and submits partial proof, commonly called shares, to demonstrate their contribution. When the pool successfully mines a block, the reward is distributed among the participants according to the pool's payment system and the amount of work each miner contributed. Pool mining provides smaller but more frequent payments. Solo mining offers the possibility of keeping the entire reward, but payments are extremely unpredictable. Mining pools do not physically merge all mining machines into one location. Miners can participate from different countries while connecting to the same pool server. Pools improve income consistency, but large pools can also create decentralization concerns if too much of the network hash rate becomes concentrated under a small number of pool operators. Mining is one of the core security mechanisms used by proof-of-work blockchains. Its first purpose is to verify transactions and prevent double spending. Because miners and nodes independently check the same consensus rules, users do not need to trust a central bank, company, or payment processor to maintain the ledger. Mining also creates an ordered history of transactions. Each block contains the hash of the previous block. Changing an older block would also change its hash and break the connection with every block after it. An attacker attempting to rewrite the blockchain would need to redo the proof of work for the modified block and all later blocks. The attacker would also need to catch up with and overtake the honest network. This becomes increasingly difficult as more blocks are added. That is why additional confirmations make a transaction harder to reverse. Mining also aligns financial incentives with network security. Honest miners can earn block rewards and transaction fees. A miner that creates an invalid block wastes electricity and computing resources because other nodes will reject it. However, mining has important trade-offs. Proof of work requires specialized hardware, large amounts of electricity, cooling systems, and infrastructure. The security benefit comes from the real-world cost of producing proof of work. In summary, mining combines transaction verification, cryptographic hashing, competitive computing, difficulty adjustment, decentralized validation, and economic rewards. Mining is not simply the process of generating new coins. It is the mechanism that helps keep proof-of-work blockchains secure, decentralized, transparent, and resistant to unauthorized changes. Thanks for watching this video, guys. Please share, like, and comment below. Also subscribe to my YouTube channel for more videos.